Okay, given that our lab this week is on batteries and making your own battery, I want to tell you a little bit more about the model we use to think about batteries that'll be useful to you as you proceed with the lab. This is the schematic illustration of what a battery is. It has these alternating lines here that are associated with the plates of different types of metal that are normally within a battery in some sort of a solution. And you'll be actually making a wet cell today that illustrates something like this. You'll see a couple of plates in there that you'll put in a solution of something. But in reality, what this battery is, we think of it as being an ideal battery and a resistor. Now, an ideal battery is a battery that will always produce the amount of voltage it's supposed to produce. A 9-volt battery will always produce 9 volts if it's an ideal battery. No battery is perfectly ideal. And what makes a battery not ideal is when it has a little bit of series resistance in it. So what we can do then is we can rewrite this battery as one that consists of an ideal battery that I'll draw right here. The ideal battery is often called, it's written with a script E, and the E stands for something called electromotive force, but you can just think of it as being an ideal battery. But in series with the ideal battery is an internal resistance. I'll call that Ri. So that this actually here constitutes everything that you see above it. So the terminals here correspond to the same terminals here. Now this resistance, this internal resistance, the bigger it is, the more your battery is going to deviate as you put other resistors in here. So if it's a really small internal resistance, then your battery isn't going to be affected as much by whatever you put over here, which is often called the load. And the load will be some sort of a resistor. You'll be using different resistors today as your load to try to figure out what this internal resistance actually is going to be. Let me give you an example. So create a new slide. So I'm going to draw the same circuit I just had in the last slide. It looks like this. It'll be the ideal battery. Which I'll denote by that script E. And let's just say for simplicity that's a 10-volt ideal battery. Okay? And that there's an internal resistance here. Let me make it look like it's more internal. But it is just a resistor, just like any other resistor you've ever seen. It's just not a resistor you can change because it is part of the battery. So you're stuck with it. No matter what you want to do, you're stuck with this internal resistor. Alright? And so here's your terminals. And what you're going to put on the end of your terminals here is another resistor, which I'll call the load. And this is exactly what I drew in the last slide. But now I want to figure out what is the voltage drop going to be across this load. Of course, it's going to depend upon what the internal resistance is here. So let's try for an example. Let's just say that we have an internal resistance of 1 ohm. It's a small internal resistance. And let's say that the load resistance is equal to 9 ohms. Now if this internal resistor was 0, and this was a perfect battery right here, then you should expect to see 10 volts across this resistor. So if the internal resistance equals 0, then voltage across the load would be equal to 10 volts, which is the size of the battery voltage here. Okay? However, since we have this internal resistance of 1 ohm, we could use voltage division to figure out what the voltage across the load would be. Voltage across the load is going to be equal to the source voltage, which is 10 volts, times the resistance of the load divided by the resistance of the load plus the resistance of the internal resistor. And if you wonder where this equation came from, I gave it sometime last week. We tended to find the current through this circuit, which would have been this term right here, and then multiplied that by the load resistor. So this here is like your I. So this is just Ohm's law, V equals I times R. But I don't actually have to calculate the I now. I can just plug in V source divided by the load resistor plus the internal resistor, multiply that by the load resistor, and get the voltage across the load. So now we're going to see that the voltage, instead of being 10 volts, is 9 volts because of the internal resistance here, taking one of the volts from the load resistor. Now, just for the sake of argument, what would happen if this load resistor, rather than being 9 ohms, let's say it was 99 ohms instead of 9 ohms. If it were 99 ohms, then the voltage across the load would be 9.9 volts. So the bigger this resistor is here, the closer the voltage drop across it is going to be in terms of how close it is to the battery. Alright, so the bigger this resistor is, the closer it's going to represent the value of the battery. To the point where if you have no resistor there, for instance, if I just took a meter and measured what the voltage drop is across those two terminals with no resistor there, in that case, it would be 10 volts. Because that would be like there is an internal resistance, there's a load resistor of infinite size. So if you look at this equation, infinity divided by infinity times some number V source, it's V source times 1, and the load resistance, the load voltage drop is going to be the same as the source voltage. Okay? You'll need to know that because in lab you're going to be trying to find this internal resistance as you change resistors over here, or load resistors. You'll be able to figure out what the internal resistance is of your system. So, let me just give you another example here. Let's say that instead of an internal resistance of 1 ohm, that my battery is starting to die, which happens. And one model of a battery dying is that the internal resistance gets bigger and bigger. So let me do the same problem that I just did. I'll create a new slide. Instead of using an internal resistor of 1 ohm, I'll say that the internal resistor is 5 ohms. But I'll keep everything else the same. So if my battery here, 10 volt battery, my internal resistance is 5 ohms, and my load resistor, let's just say, is the same 9 ohms that I had earlier. So now the voltage drop across the load, which had been 9 volts a little while ago, now that my internal resistance gets bigger here, that's the only thing that's changed, my voltage drop across the load is equal to my source voltage times this ratio of resistances, that's the load resistor divided by the internal resistor plus the load resistor. That is equal to 10 times 9 divided by 14. So 90 divided by 14, that's a lot less than 9 volts now. It's going to be something like, it's about 6.7 volts or something like that. This is what happens when your battery dies. When your battery dies, this value doesn't change. The load resistor is still going to be whatever it was before, but what changes is the internal resistance, which goes up and up to the point that your load voltage gets smaller and smaller, and your lights start to dim in your flashlight, for instance. Okay, so one last thing I want to mention to you that'll help you with your lab is you're going to be thinking about the internal resistance of both a D-sized battery, which will look something like this, okay, there's your D-sized cell, and then your double A size battery. Your double A size battery would look something like this. Now I'll ask you, which one do you think has a greater internal resistance? You'll actually try to measure that. But as a hint, I'll tell you this. The D-cell battery has plates that are much bigger than that double A cell battery. So there's actually more places that current and charges can flow in your D-cell battery than in your double A cell battery. So that means that there's more resistance to the flow in the AA size battery. So I would expect that the internal resistance would be larger here. You'll get to see if that's the case. Of course, if it's a weak D-cell battery, if it's not a fresh one, then I wouldn't necessarily be able to make that argument. So I'm hoping that we have fresh batteries to use in today's lab that haven't been used before, in which case you'll hopefully be able to see that the internal resistance of the AA cell size battery will be bigger than that of the D cell. Okay, enjoy the lab.